This video will cover molecular interactions, which of course is the basis for drug action. And the types of molecular interactions, when we talk about drug action, is a drug interacting with some target. Now, in most cases, it's a protein, so protein-based receptors, channels, enzymes, and so on. Drugs, of course, in order to get into the system, in order to be able to interact with the target molecules, it interacts with water, and as it crosses membranes, right, it would be drug-lipid interactions. Some drugs can interact with DNA or RNA, and then, of course, drugs can, at times, interact with other drugs as well. So these are all the types of things where we have to consider how this occurs. Just as a quick summary of a lot of the types of things that we call receptors or targets for drug action, we have very specifically the message receptors. So this is a normal type of thing that we talk about when we talk about receptors, right? We're talking about neurotransmitters and the G protein coupled receptors that they bind to, or ligand-gated ion channels. Okay, that's the typical type of thing we have, particularly in the CNS as well as the periphery for neurotransmitters. Hormones, which are nothing more than chemical molecules which act more remotely from the site from which they are secreted most of the time, can be peptide or protein in nature. Immunomodulators, nuclear receptors, so these are receptors that affect the nucleus and basically how the cells respond. And so steroids, thyroid hormones are examples of these, vitamins A and D. We have enzymes, which are targets, both kind of in an active sense and a passive way. So from the standpoint of drugs interact with enzymes, if they are intended to be, say, enzyme inhibitors or modulators, the enzymes that it interacts with kind of in an unintended way, but we do study it and it's important, are the metabolizing enzymes. So when it gets into the body, how it's processed. As we said, nucleic acids, excitable membranes. We talked about ligand-gated ion channels here, associated usually with neurotransmitters, and these are voltage-gated ion channels. A whole variety of others. We have transporters, which of course are proteins. We have for both active and passive. And then of course, basically a drug could potentially interact with bone itself. So, not necessarily a protein, and other types of things. So these are just kind of to show you the broad array of types of things that we're talking about. Now, when we talk about bonding, normally we think about covalent bonding, right, which is how one atom is tied together within a molecule. This is not what it's not really the subject of this video. Covalent bonding really just relates to how molecules are made up. And covalent bonding can occur in certain type of enzyme inhibitors called suicide inhibitors or irreversible inhibitors. But this is not really the matter of the subject here, okay? So what we're talking about are reversible types of bonds. So non-covalent, in other words, it's two different molecules that are interacting but not becoming another molecule. So these are basically either electrostatic interactions or induction dispersion interactions. And we have them ranked on this chart in terms of relative strength. So you can see there's more kilocalories per mole associated with ion-ion interactions than if we go all the way down to many less kilocalories per mole associated in induced dipole interactions. Now, what's the main difference between all of these? We have ion-ion, ion-dipole, ion-quadrupole, dipole-dipole, quadrupole, a special type of dipole-dipole called hydrogen bonding, And then we have different combinations with induced dipole, which is either ion-induced dipole, dipole-induced dipole, or induced dipole-induced dipole. We'll explain what we mean by induced dipole. But essentially, these are uncharged, neutral molecules that develop a dipole only because they are next to one another. Okay, so hence induced dipole. So this is something that is extremely weak and only has a very weak partial charge. Ions are full charges, right? So normally type of thing we talk about a plus minus charge, right? Associating with one another. A full plus one and a full minus one charge. A dipole, right, has a partial charge, right? It basically has a partial positive and a partial negative within the molecule itself. So those partial positive or partial negative charges can interact with the corresponding opposite charged ion. Okay, so here we have a full charge, right, and a partial charge interacting. So full, 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 partial, and then we get the dipole, dipole, we have partial, partial. Now quadrupole, we'll explain what this is and show pictures too, is really just a more complex dipole. So it's very similar to a dipole. And the strength actually turns out to be very similar. You'll notice dipole, dipole is this strength, 1 to 5 kilocalories per mole. Quadrupole, quadrupole is 0.2 kilocalories per mole, but notice the little asterisk. The asterisk means it's per heavy atom. So usually in a quadrupole, you're going to have, say in a benzene ring, which is an example of where we can have a quadrupole, there are 6 atoms there. So what does that mean? 6 times 0.2 is 1.2, which actually puts it in this range, right, of the dipole, dipole. So it's really similar. The induction dispersion, now we're talking about very weak. So this is a partial charge, right, and this is a very weak partial charge. So we either have a full charge and a very weak partial charge, a partial charge and a very weak partial charge, and then 2 very weak partial charges. So again, the strength of the interaction goes down as we go down this list. So as the charges become less, the interaction energy becomes less. So if we're looking at all of these kind of in a group, you just basically say the strength of the charge, right, is going to determine the strength of the interaction. Now, the only thing that seems and acts a bit odd are hydrogen bonds. And technically, they're a dipole-dipole interaction, but they have bonding characteristics that are unique. And so we are going to talk about this separately, but you can see the energy for it is slightly higher than what we have for a typical dipole-dipole interaction. Okay. So the question is, we have all of these, and some of these, like the dipole-dipole and its corresponding quadrupole-quadrupole, are called Keesom interactions. Dipole-induced dipole are Debye interactions, and induced dipole are sometimes called London interactions. These are named for the person who basically first described them. So that's all that these mean. Now, you may have heard something else down here in the corner. It says, what about van der Waals? You've all heard, if we take an organic chemistry, right, or even biochemistry, van der Waals interactions get brought up. So the question is, what is that? The problem in many cases is van der Waals interactions are often described in different ways, and some people consider different of these to be van der Waals actions. Sometimes they're only talking about essentially the equivalent of London interactions. So let's do this formally and try to understand what are van der Waals interactions. What do we consider in that category? So first of all, who's van der Waals? He was this person who tried to describe molecular interactions, basically. Very simply, this topic that we are talking about. And so he tried to understand this attraction as a force, right? So what is a van der Waals force? Well, he obviously had particular intentions, and this has been discussed by organizations as to what this is. But sometimes, the meaning gets obscured, and sometimes people describe it as all forces, whether they're attractive or repulsive. Sometimes it's just talked about, wait a minute, it's only attractive forces. And some people just describe it as, it's only these two neutral compounds coming together, right? It's these very low charge, or we can almost consider virtually non-charged type things that interact with one another. Essentially, none of these is completely correct. So what is the best way to describe this? The best way to deal with things when we have something that kind of through history the meaning gets kind of diverted in several ways is you have a group that gets together and decides, okay, what is the orthodoxy here? Just like in religions, basically, different books come out, different opinions come out, and at some point people have a conclave or some other type of convention, right, to say, hey, they have their discussion, they hash it out, and then finally somebody says, okay, this is what it is. So we have that in chemistry. It's called UPAC, the International Union of Pure and Applied Chemistry, which normally we talk about as, that's chemical nomenclature, right? Well, it's also talking about a few other things. It defines terms and terminology within chemistry as well, and one of these things is van der Waals forces. So we can see one of these things that was on that previous slide, attractive or repulsive forces between molecular entities. Now, the key thing that I want to point out here that makes it real easy to understand is it's these attractive or repulsive forces other than those due to bond formation, right? So it's not covalent, or due to electrostatic interactions of ions or ionic groups with one another or with neutral molecules. Okay, what does this mean? Anytime we see, so basically what it means, we're not talking about covalent bonds, which we weren't, okay, we know that. And we're talking about anything other than if we see the word ion in it. In other words, if we see an interaction and it says ion, that is not a van der Waals interaction. So what is included here? So a van der Waals force includes dipole-dipole, dipole-induced dipole, London, and of course we have a few others described on the slide that are kind of like variations of this, right? So we're not interested in the loosely applied. This is the formal definition up here. And basically, the way to read this is to just basically say it is all types of molecular interaction that are non-covalent and don't have as part of its contributing group an ion. Okay, so what does that look like in terms of our chart? So here's our chart redrawn considering van der Waals interactions, and we've labeled them on the right here which ones we consider van der Waals interactions, and the others of course are not. So of these, you can see we see the word ion here, we see the word ion, those are not, which hence we have not labeled those as van der Waals. Dipole-dipole, well, that was specifically stated in the UPAC definition, right? Quadrupole, which quadrupoles are a type of dipole. We'll explain what the difference is, but basically it's a type of dipole. And then when we get down to induction dispersion type interactions, well, dipole-dipole were, right? So dipole-induced dipole certainly will be, as well as induced dipole-induced dipole, which again, the UPAC definition specifically mentioned, right? So we have these four types, right? The common thing being that they don't mention the word ion are van der Waals interactions. Now, notice we have one other we don't have labeled, and that's hydrogen bonding. And hydrogen bonding, even though we can kind of subclassify it as a dipole, is its own animal. And a hydrogen bond is not a van der Waals interaction, okay? Because there's a difference that we'll talk about here that really makes it distinct. Okay, so let's get on to one thing that was on that chart that is a characteristic of these different types of interactions, is how the interaction energy varies with distance. Okay, so this is shown the potential energy of a compound, and this potential energy changes, okay, as we get farther away from each other, right? So if we have two molecules, they cannot be at distance zero. Distance zero is a complete overlap of the atoms, and they cannot occupy the same space. So clearly it can't be zero. So what is this place where it starts? It starts here at what we call a van der Waals distance. Okay, and the next slide will actually describe specifically what that is. But this is the distance of closest approach between the two atoms. If we try to go any closer than this, repulsive forces rapidly ramp up and the two atoms push each other away, and this is the place of closest approach they can be. So now beyond this point, right, we have attractive forces right here that are holding them together. As we move them farther apart, right, moving to the right, we have basically a decrease in the attraction, right? And eventually that attraction will go to zero, which is at the top here. So the question is, when we have different types of interaction here, ion-ion, ion-dipole, dipole-dipole, right, they drop off at different rates. Okay, so if we go back to this other slide, you can see we have this column about distance dependence. This is referring to that chart. Ion-ion interactions decrease directly proportional to their distance, right? It's 1 over their distance. So if they're twice as far apart, they have 1/2 the interaction energy. It's that simple of a proportion, okay? In an ion dipole, it's 1 over r squared. So if they are twice as far apart, that means we have 1/4 of the interaction energy. Okay, so you see how that works? And dipole-dipole, it's 1 over r cubed. So if we have twice the distance, so r is 2 times of another value, right? This will be 1/8 the strength of interaction, right? 2 cubed is 8, and so on. And this relationship just basically means exactly that. As we change the distance, right, the rate at which our strength decreases basically is more drastic as we go down this list. This is just showing this graphically. So in the case of our ion-ion interaction, right, that's this brownish line here. And you can see that basically as we get farther away, the strength of the interaction decreases. But even over these greater distances out here, there still is some strength of interaction. And it just drops off. And eventually it will drop off to zero if you get far enough away. Okay, so ion dipole, what do we have here? Well, that's this kind of mustard colored line. And it's dropping off more rapidly than the ion-ion interaction. And it goes then to zero, or essentially asymptotically to zero as we get farther and farther away. Dipole-dipole interaction is the green. Okay, again, faster than the ion dipole. And then the last one at the bottom, dipole, induced dipole interaction, right? As soon as we basically move anywhere away, right? So this is where, if we take this line and bring it up here, it's like right here, right on this line in terms of our distance. You can see that as we move away at all, right, the distance changes and the energy decreases in a very rapid rate, right? So by the time we're here, we have no more interaction energy. Well, how far have we moved? Look at this. If you take this down and just compare it, it's basically at twice the van der Waals radii. We have no interaction anymore. That's pretty drastic. In other words, what are we saying? That in the case of an induced dipole interaction, we actually have to have the two molecules virtually touching one another. If we separate them at all, we lose the strength of the interaction. All these others can have a certain amount of affinity over a certain distance, even if they're not in direct contact. Okay? And some are better than others. Obviously, ion can act over the greatest distance. Okay. Just want to hammer in that concept because I don't want to make these terms abstract or the things that are on the slides abstract. I just want it to be as clear as possible. So what are we talking about with this minimal distance of approach? So this here, right, if we look at these two atoms that kind of are fused here in the middle, this is a molecule that has a covalent bond between these two atoms, right? So the molecular orbital is such that their individual orbitals, right, can overlap, and that's part of the nature of the formation of this bond. When we have a non-covalent interaction, these orbitals here that we have for the molecular orbital here does not overlap with the molecular orbitals here of the other molecule. So if these two molecules are next to each other, the closest they can be is at this van der Waals distance, right? Which is the sum of the van der Waals radius of one molecule and the van der Waals radius of the second molecule. It will be the van der Waals distance between the two molecules. Okay, and that's on the previous slide. Remember, that distance is this distance of closest approach. So this is that van der Waals distance right here. Okay. So that's the whole concept of what we're talking about here with regard to non-covalent interactions do not overlap these orbitals. And so when we talk about any greater distance, we're talking about moving this molecule away from this, and we're creating a gap in between them. Now, as we do this gradually, right, nothing can occupy this because no other molecule is small enough to fill that gap. But eventually, when we move two molecules far enough apart, there's some point where a solvent molecule can fit in between. And then these will end up being separated by one solvent molecule, and as we move it farther away, multiple solvent molecules, right? And as we'll show, that's going to then basically greatly decrease the interaction that these two things can have because the solvent molecule that's in between acts as an insulator. It shields the effect that we get. And so that being the case, these molecular interactions that we're talking about are over short distance because the other thing with this chart is this potential energy we're talking about is also potential energy in a vacuum. So this is essentially how it drops off if we don't have any solvent that can get in the way and interfere. Okay, so Again, just quickly summarizing, these ionic interactions are the strongest of our known covalent bonds. Traction of ions with opposite charges, right? A plus charge and a minus charge. These are full charges, and so therefore gives us the highest possible interaction energy. The ion dipole, right, is an ion in a partial charge of a dipole. So it's, say, a plus ion, a full plus ion, and a partial minus ion of a dipole. Or it's a full minus ion, and it's a partial positive charge of a dipole. Dipole-dipole, right? It's these partial charges of two dipoles in two different molecules, right? And the opposing charges, the partial positive and partial minus, are coming together and interacting. Hydrogen bonding is a dipole-dipole interaction where one of the constituents is a hydrogen. It is attached to a heteroatom, and in this case it's going to really be either a nitrogen or an oxygen. And then in the second molecule, a lone pair of electrons of a nitrogen or an oxygen then are non-covalently bound to this particular hydrogen, right? This hydrogen is covalently bound to a nitrogen or oxygen, and then that hydrogen that is attached to that heteroatom is interacting with a lone pair of electrons of a second heteroatom, nitrogen or oxygen. Debye or London effects, right, is a dipole, that's the Debye, or a temporary dipole, which would be the London interaction, essentially producing a temporary dipole in another molecule. And that's why we use the term induced dipole. We'll have a little cartoon showing how this occurs. Okay, so pure ions, two examples are shown up here in the top. So we have a cation, which is a positive ion, or we have an anion, which is a negative ion. And the electric field is basically showing that the vectors of the electric field are pointing away from the positive charge. In terms of one way to interpret this is these arrows are in direction of where another positive ion would be pushed if it was in this vicinity. So let's take our little dot here, and let's say we had it here, sitting here. Okay, which direction would this positive ion that's represented by my red dot here go? It would be pushed in a direct line away from this cation here. And that's true in all directions, not only in this plane, but in the entire sphere around this ion. So this does not have any direction whatsoever. In other words, wherever we are relative to this cation, another positive charge will be pushed away from it, directly away from it, right? Not at an angle, not across from it. It will be pushed directly away. Whereas in this case, again, this is showing the electric field, and the arrows are pointing towards it. And what this refers to is if we have a positive ion, again a cation, they will be attracted to this minus ion. And depending on where it starts out, let's say it starts out here, right, it will be attracted directly towards that minus ion. So it's going to follow these electric fields, right, directly to the other ion. And again, this is represented here in a two-dimensional diagram, but this operates three-dimensionally in a sphere. In other words, from any direction, the positive ion will move in a direct line to where the minus ion is until they reach their closest approach. So that's how to interpret these lines. Now, an electric field in a dipole is a little more complicated. And you may have seen things like this, like if people put a magnet behind a piece of paper and then they throw iron filings on that paper, they kind of arrange in these arc-like shapes. So what that is those iron filings are aligning themselves with the magnetic field lines. In this case, in an electric field, right, this is basically showing the same type of thing that we had up here, but it's showing interaction with a cation and an anion. Of course, these are partial charges in a dipole, okay? So it's weaker. But if we had, just for example, again, this red dot was a positive ion. Let's just say this positive ion was very close to this partial charge in this dipole, right? The positive ion, we get pushed away from the cationic portion of the dipole. And so which way is it going to go? Well, normally it goes directly away, but notice this group over here is going to influence it somewhat. It is going to influence it by trying to attract it. Now, this is going to want to push directly away, and this is going to want to pull it directly. But with the combination of those, it's not going to go in a straight line from here over to here. What it's going to do, right, is first the force of repulsion to this charge is greater than the attraction that we get from this charge, because this is much closer and this is farther away, right? So what's going to happen is, since the repulsive force is greater than the attractive force, it's going to have more of an effect. So it's going to tend to push away more than it's being attracted to that minus charge. And it's going to push away, push away, push away, until now we've weakened this repulsive force now that we're farther away. And the difference between the distances between the two cations and the cation and the anion now are not that much different. So it's going to start moving towards that minus, right, ion part. And it'll essentially move along these electrical field lines. So this is a description of the path that an ion would take if it was near this dipole in order to get closest to the partial charge that is opposite of the ion that is in question. So again, we're saying this is a cation that we have here for this red dot, and it will move along these electric field lines until it gets over here to its place of closest approach. Okay, so that's what it is. So when we have these two charges, right, we have a mix of attractive and repulsive forces. When we are, right, anywhere in the middle, right, anywhere right where this line of arrowheads is, right, we are at an equal distance between the two, right? So the repulsive forces along this line and the attractive forces are equal. And so therefore you can see that's when the direction changes of it really going much more towards directly the minus ion. Okay, so we go from here, on this side, right, the repulsive forces are greater than the attractive forces. When we get to the midway point, they're equal, and here the repulsive forces are weaker than the attractive forces. Okay, so that explains why the lines are curved like that. So what are we talking about when we talk about ions? Okay, when we talk about ions, they of course are either electrolytes in solution, they could be attached charges to molecules, and in most cases what we're going to be talking about are what we mentioned with regard to the functional groups. So we're talking about ions in the drug molecule and then ions in the receptor, for example. So in our drug molecule, we can have a variety of functional groups: carboxylates, sulfates, sulfonate, phosphates, and so on. We, in proteins, have side chains that can be anions, and that's deprotonated glutamic acid or aspartic acid, right? These are carboxylic acids that are in the side chain. So these can be our minus charges in a drug molecule. For positive charges in a drug molecule, we can have things like the functional groups that are bases, right? We have his, arg, and lysine, as well as the amine terminus, which is an amino group of the peptide chain. The functional groups in heterocycles, right? We can have guanidiniums, imidiniums, pyridiniums, imidazoliums, and as we mentioned, heterocyclic bases as well. So those could be our potential cations. So minus charges and plus charges. So what we're largely talking about is our anions are acids that have lost a proton, and our cations in these cases, right, are bases that have a proton on them. In other words, they're the conjugate acid. This is what we mentioned about the distance between our charges now. This R distance that was in that one chart, right? And if our distance is essentially smaller than the diameter of a water molecule, there is a vacuum in between, right? And so our interactions between these two charges or partial charges is going to be greater. If we now put a solvent in between, that solvent can be either polar, the solvent can be, in other words, a dipole, or it can be a hydrocarbon. In either case, we're going to have a certain amount of what we call shielding that takes place. In other words, what it is the solvent molecule is now interacting with these charges, and that interferes with the direct interaction of these two charges with one another because of this interaction with the solvent itself. Now, certain solvents will interact with ions better than others. The ones that interact with ions better than others are either charged things, charged molecules, or polar molecules. And the example of a polar molecule is water, right? It's one of our more polar solvents. And we assign a value, this is called a dielectric constant, that is a high number compared to other solvents that could be used that are less polar. All the way down to up here we have hydrocarbons, and you can see this number is substantially lower than water. So we go from water, right, to formic acid, to methanol, and then hydrocarbons. And we can see we are stepwise moving down in this dielectric constant range. And this has to do with the level of polarity that we have in these. So water basically is the most polar, and then we get down to other things that are less and less polar, right? Some of these things, particularly these organics, right, have methanol is probably the easiest to compare to water, right? So water is hydrogen hydroxide, right? It's a hydrogen with an OH attached to it. Methanol is a methyl group with an OH attached to it. So the difference between water and methanol is instead of hydrogen here, we have a CH3, which is attached to the OH. So you can see this is going to be less dipolar, right? Because the methanol oxygen difference in terms of the carbon oxygen difference in terms of electronegativity, right, is less than the difference between oxygen and hydrogen that we have in water. So that's where this ranking comes from. And so what it amounts to is the minus part of the dipole, so this would be like the oxygen in water, is going to associate with this cation component, whereas the hydrogen component of water, right, which is going to be partially positively charged, is going to act with the anion in the solution. And you can see how the solvent molecules orient themselves around each of these ions such that the opposing partial charge of that dipole is what's interacting with the ion in solution. So we have these partial minus charges with the cation, and the partial positive charges with the anion. Okay, so we get this orientation of the solvent molecules, and as well as they intervene in between and have their partial charges aligned. So just the long and short of it is shielding weakens interactions. It decreases the strength of an interaction as you increase the distance by much more than you would have in just a vacuum. Dipole-dipole interactions now are more complex than simple ion-ions. Ion-ion interactions, the energy is a simple function of the distance, right? It's 1 over r squared. Now our energy is more complex. Because why? Because a dipole is much more complex than a single point ion. In the case of acetone here, interacting with acetone, we have to take into account, one, we can not only have interactions between this partial minus charge with this partial plus charge, which would be attractive, but we also have an interaction of this partial minus charge with this partial minus charge of the other molecule, which is repulsive. And we have to account for the fact that these have different strengths of effect based on their relative distances. So what's going to basically give our total overall energy, right, is going to be a function of how these two groups are oriented to one another, what their distance is to one another, and their orientation is defined by 3 different torsion angles. Basically, it's defined by, 1, how this group is rotated in 3-dimensional space relative to this other group, which can also be rotated in 3-dimensional space relative to this. And hence, that's these torsion angles 1 and 2 here. So they can either be kind of the way they're shown here, right, flat in a plane next to each other, or they could be face to face. In other words, turn both of these 90 degrees where they stand, and it's like 2 hands now facing each other to clap, right? And you can imagine those could get potentially closer together. So that's going to affect the strength of the interaction. This, of course, then is also what is the angular distance between this carbon-oxygen and this carbon-oxygen. In this case, we're showing these two to be opposed to one another, right? They're in the opposite directions from one another. So if we considered this a torsion angle, we could consider that this molecule, if it was identical over here, is now rotated 180 degrees so that the oxygen's at the bottom and the carbonyl carbon is at the top, as opposed to being at the bottom here and at the top here, right? So this angle defines this relationship. So if we define these angles, we can basically do this along with some constants, and the distance cubed, remember this was the strength of the interaction was 1 over r to the 3, so this, notice it's the denominator. And then as a function of these angles here, in both a positive and negative contribution, depending on the repulsive forces versus the attractive forces, right? We also have repulsive forces for the slightly positive versus the slightly positive. So that's why we have these factors and then a minus and then that factor. So that's how the equation comes out. You don't have to know the equation, but basically the orientation is critical here. So if we have a carbonyl group again, like this, right? If we have a minus charge ion or dipole or something else like that, it's going to want to be somewhere over here by this carbonyl carbon, right? It's going to want to find itself either over the top right? Or down over here, anywhere, right? Kind of in a whole hemicircle around this. But if it's a minus charge, it's not going to want to be sitting up over here, right? It'll want to get pushed away over a little bit because it doesn't want to be close to this partial minus charge, right? So if we had this partial minus charge, it's going to be repelled if it's over here. It's going to be completely a negative interaction. Here, it's going to be kind of neutral from the standpoint it would be repelled by this, right, but attracted by this, because the distance is equal between the two, right? And same as we go out all the way out here. So really, a minus charge is going to be wanted somewhere in this half of the molecule, right? Somewhere over here. Whereas a positively charged molecule or positively charged portion of a molecule, right, is going to want to orient itself somewhere over here. It's as simple as that, right? It's just charge, charge, attraction, or repulsion. So this is showing two other carbonyl groups. In this first one, notice they're oriented in the same direction. Remember, we had that one torsion angle, or we could have these oriented like this, or we could turn it around 180 as we showed in the previous slide. Okay, so we're talking about this situation. And notice we have a slight positive here. We're going to have the corresponding slight positive here. So this is a repulsive interaction. So I've drawn it in red. This is a slightly negative charge here. This is a slightly negative charge here. So I've drawn this repulsive interaction in red. Okay, so they are at a particular distance to one another. Now, if we look at the attractive interactions, the attractive interaction is this slight positive to this slight negative, and this slight positive to this slight negative. We've drawn these attractive forces in green, but I've made it a less intense green because the distance between the attractive forces, right, is greater than the distance between the repulsive forces. That means when we add all the energy together, this is going to be a net repulsive interaction, right? And these two molecules are going to push away from one another. So this is a repulsive net interaction. If we look at the situation where we turn this dipole in the other direction, right, we have our slight positive here, slight negative here, slight negative here. Now we can look at the attractive forces, and I've drawn that in green here. Slight positive, slight negative, slight positive, slight negative attractive force. And the repulsive forces, right, I've drawn in orange, so it's not as intense as it was in the case on the left. These are farther apart than the attractive forces. The distance between this slight negative and this slight negative is greater than the distance between this slight negative and this slight positive. So I've drawn these as a less intense color to indicate that they're weaker. Okay, so what we have are two stronger interactions and two weaker interactions. Net, this is going to be an attractive interaction because our attractive forces are greater than the repulsive forces. And that's how this is determined, right? So there's going to be optimal situations and orientations for these. In this particular case, this is over to the side, so it's going to have a particular strength, but actually it would be a little weak. The strongest possible interaction, I won't have shown on this slide, but basically imagine taking this version of acetone and basically moving it completely overlapping, and you can't be in the same place, but it would be flat over the top of this. Right? So taking these two, imagine this is your left hand with your palm facing towards you, and this is your right hand with your palm facing away from you. And now what you're doing is you're moving the two of these together where your two palms are over one another, your two palms. And that's kind of what you have for the best situation where the two flat sides of this molecule are over each other and they're turned 180 degrees like shown in this picture, so that the maximal amount of attractive force can be found and there is a minimal distance for this attractive force, because that gives the strongest interaction. Okay, so it's going to be that face-to-face that's going to be the best for this particular molecule. Okay, hydrogen bonding. Hydrogen bonding is an interesting thing. Hydrogen bonds are dipole-dipole interactions, right? We have a dipole. So in this case, we're showing two alcohols. We have an OH bond. Oxygen's more electronegative than hydrogen, so this is slightly negative, this is slightly positive. This is slightly positive, this is slightly negative. We have here this slightly positive charge on this hydrogen interacting with the lone pairs of electrons of this slightly negative oxygen. So we have, right, an electrostatic interaction between the two. Now, if, as for a typical dipole-dipole interaction, these could only approach to within their van der Waals radii, then the closest approach would be 2.68 angstroms, right? So it's the van der Waals radius of the hydrogen, which is smaller than the oxygen, which is 1.5 angstroms. So we would add those two radii together to get the van der Waals distance. When the hydrogen bond is actually measured, right, it can be somewhere less than 2.68 angstroms. It's a common number is about 1.76. Often we think about a good hydrogen bond as something, 2 or less. Okay, when we measure this, where do we measure this? We actually can look at this in a crystal structure. We can actually measure this distance accurately from something like that. So what does this mean? A typical OH covalent bond, so this bond here, the OH, when it's not interacting with another molecule, right, is normally 0.96 angstroms. So this is a covalent bond. This is a complete typical non-covalent bond where there's no overlap of the orbitals. So a hydrogen bond exists somewhere in between these two. It is not a covalent bond, but this hydrogen is shared between the covalently bounded oxygen and the non-covalently interacting oxygen. So we talk about this hydrogen being shared. There's a couple consequences of that. One is that lengthens the length of this OH bond, and we depict the hydrogen bond usually with some type of hashed lines. Characteristics. It is directional and short-ranged. Okay, let's go back to this slide to kind of show a little bit of this. So it is directional and short range. So the short range is that this needs to be close enough together to have the interaction, right? And this actual interaction distance varies a little bit, but basically it's on this order of 1.6 to 2 angstroms, less than just the van der Waals radii. So that is your typical hydrogen bond. And we say variable because this length can be a little bit different. And that's going to affect the strength of the interaction as well. So the strength of hydrogen bonds is a bit of a variable thing. What causes this variance? Well, one is distance, another is the angle that we have between this OH bond, right? So this is a vector, it's a line, and the vector or line that we have between the oxygen and its lone pairs of electrons relative to this vector. If we have complete alignment of this oxygen, hydrogen, lone pair, and oxygen, all in exactly a straight line, that is going to be the strongest interaction. So that's what we mean by directional. If we rotate, say, this alcohol, these are two different molecules, so this could be just rotated in space, and the lone pair of electrons can still be interacting. But let's just say it's moved out of plane a little bit and is over here, we're still going to have a hydrogen bond. It's not going to be as strong because it's not as optimally aligned as a one where we have it aligned. That's all we're saying. So, and then again, that's another feature that leads to the variability of the strength of hydrogen bonds. Okay, so it's directional. It's based on these bond orientations. It's short ranged. It has to be within that particular distance where we get an overlap of the orbitals. The ideal angle is normally close to 180 degrees. And this hydrogen bond distance is significantly longer than a covalent bond, right? Remember we said covalent was about 0.96 and our hydrogen bond was about 1.76 or something in that range, right? So it's about, what, 0.8-ish in that angstrom difference, which is a pretty big difference. The covalent heteroatom hydrogen covalent bond is lengthened. So we mentioned this because the other heteroatom in its lone pair is having an interaction with this hydrogen and actually pulling on it and weakening this bond interaction a little bit. So this gives this lengthening, and the strength of that leads to a change in the stretching vibration. The change in the stretching vibration is to longer wavelength, and we call that a redshift. And of course, we can observe this in things like infrared spectroscopy. So that's a way we can actually observe what's going on here. So when we have hydrogen bonding, we can see this in the spectra of its compounds. The stretch that we get, so it's the vibration that's associated with the heteroatom covalent bond hydrogen stretch band in our infrared spectrum, becomes broader and stronger. Okay, what does broadening mean? Broadening means that our resonance frequency is not as precise. It means it's more variable. And where does that come from? That comes from the fact that we have a variation in the strength of our hydrogen bond, right? And so the exact frequency at which we get this resonance is happening at different frequencies. So the band that we observe is broader. Okay, in an NMR, this essentially, a hydrogen bond results in deshielding of that particular proton that's involved in the hydrogen bond, which will shift its signal. It'll shift where it happens to be in our spectrum. So in other words, if we have a very dilute solution, say, of our material, and it's not involved in a hydrogen bond, then the signal will be at one location. If we have a very concentrated sample, and now the molecules are, say, hydrogen bonding to one another in that sample, we will observe this deshielding, and this NMR shift will be at a slightly different location. So it's the same molecule in solution, but sometimes the concentration at which we take this sample, right, we can observe that signal for this proton in different places, and that's due to the hydrogen bonding that's taken place in solution. Typical hydrogen bond strengths, 2 to 5 kilocals per mole. And the heteroatom that we have in a hydrogen bond, as we said, is either an oxygen or a nitrogen. Now you can ask, well, what about sulfur? Sulfur, right, exists very similar to oxygen, right? It's just directly below it in the periodic chart. It has lone pairs of electrons, right? It is a different electronegativity, right, than the carbons are, and so on. But it's a much larger molecule, right? And its shell is much larger. It type of interactions that it has, so its lone pairs with the hydrogen that's attached to another heteroatom, is very weak. Since it is weak, we're not considering it as important for drug interactions, right? So theoretically, we can talk about, what can happen, and we can probably quantify it and all this. But the point is, we're trying to understand molecular interactions from the standpoint of drug properties. And so therefore, which functional groups in a drug molecule have certain types of molecular interactions that are important, right? That are quantifiable in a way that makes a difference in that molecule. And so from that standpoint, we are not going to consider sulfurs here. Similar with fluorine. Now fluorine, you'll see all kinds of organic chemistry textbooks talk about hydrogen bonding in fluorine. Yes, it's real, it occurs. Fluorine is a highly electronegative atom, right? So it's going to be slightly negatively charged, right? That being the case, we only observe significant hydrogen bond strengths, right? This 2 to 5 kilocals per mole in hydrogen fluoride itself as a liquid, which does not exist in biological systems. This is an extremely poisonous and corrosive material. So where do we see fluorine in drug molecules? Well, fluorine is actually a very common means of providing stability to metabolism in drugs. And so you will frequently see drugs with fluorines in various positions of a molecule. Now, are those fluorines that are introduced involved in hydrogen bonds? You will find some papers that actually talk about that. But for the most part, these interactions are, again, very, very weak, right? These are not strong hydrogen bonds. Again, how do we find evidence for hydrogen bonds? We find evidence for hydrogen bonds from X-ray structures. I mean, we can look at spectroscopy, but when we're looking at, say, a crystal structure of a receptor with a drug bound in it, we look at, okay, what is this fluorine interacting with? Is this fluorine interacting with basically hydrocarbon groups, which means what? That's going to be like so a fluorine would be a dipole there, so it would be a dipole-induced dipole type of interaction. Or is it involved in a hydrogen bond? So what we would have to see is we would have to see something like a hydroxyl group or an amine NH, where the hydrogen is at this distance to the fluorine that is shorter than the length of the van der Waals radii and longer than the length of a covalent bond. Okay, so that's not the thing that we have typically cataloged and found, so that these are not typically involving themselves in hydrogen bonds. Fluorine substances have very unusual properties. It's often considered to be like a third phase. So highly fluorinated materials, if you have a highly fluorinated liquid, for example, right, can basically exist in a third phase between a hydrocarbon and water, right? So if you put a hydrocarbon like hexane in water, right, it floats on its surface, right? You form two layers. If we add this perfluorinated compound, now depending on what it is, we can sometimes get 3 layers. In other words, they are actually each have their own unique properties and don't necessarily interact as strongly as you might think they would. So a perfluorinated material, right, if it was involved in hydrogen bonds to a great extent, you would think would be greatly soluble in water, right? But what do we normally think of? The most common perfluorinated substance that we know of is Teflon, right? Teflon-coated pans. Well, what do we use the Teflon for? We use them as a non-stick surface. Well, what causes sticking, right? It's adhesion. And what's causing this adhesion? It's the adhesion of various proteins, like say in an egg, the egg white, or in the water, right? And the water is going to contribute to that because that's how it's going to spread on the surface of that Teflon pan. So yes, it obviously spreads out because of gravity, but if you look at the edges, say, of when you crack an egg and put it in a Teflon pan, right? The edges will be kind of bent under a little bit. They're not going to be absolutely flat out. So if it was adhering to the pan, it would be flat out. So that's like if you take a cast iron pan, don't put any oil in it, and put the egg in it, that egg is going to stick to that pan. Now, if we use a Teflon pan, we don't have to use the oil, right? It's kind of a substitute for that. And it'll still float around on the surface of that pan and not adhere to it. This is what we're talking about. So fluorine is not something that we're going to consider for hydrogen bonding. And you'll find some debate on this, and you can probably even find some papers saying that, oh, it is important. Generally, it's not. So this is maybe at the opinion stage here to a certain extent, but I think there's a lot of evidence for saying that it's not. So oxygen and nitrogen, for the sake of the way I teach and what I find useful, are the heteroatoms that are important when we're talking about hydrogen bonds. So this is an infrared spectra. Okay, a molecule is taken, put in some type of a holder or in solution, and basically light at different wavelengths, right, is shown through it, and then we look at the absorbance of that light. Now, if we have like a carbonyl group, right, or something like that, it will absorb the light, or this alkene, right, it'll absorb the light at a particular frequency, and normally we see these peaks that are reasonably sharp, right? They're not hugely broad, right? They look like peaks. And so, and that's characteristic then for, say, this carbonyl stretching, the C double bond O at 1695, right? And the C carbon-carbon double bond stretch at 1630. Now, our OH, so this is the O covalently bonded to the hydrogen, okay, should be, in an ideal situation of a pure substance, right, just existing at a particular sharp wavelength and looks something like this. What we actually observe is this huge broad band here. So what do we have with carboxylic acids? We have a oxygen covalently bound to the hydrogen. So this is at a pH where this is protonated. And this can hydrogen bond to another oxygen lone pair of electrons. And where can that be? Well, that can be either in the OH of the a second molecule of this, right? Or it can be to the carbonyl oxygen lone pairs, right? So this can hydrogen bond in a couple of different ways. So these are strongly hydrogen bonded when you have, say, this material as a pure solution to other molecules in that same solution. So that we get this spectrum. And so this OH bond, the band that we see for it is over this 2500 to 3500. It's this huge thing. And so what does that mean? The strength of that bond is highly variable because the strength of the hydrogen bonds that this OH is involved in as a proton donor is variable. And how is it variable? Why does it vary? Well, first of all, you could imagine a hydrogen bond with this oxygen lone pair versus a hydrogen bond with this oxygen lone pair might be a little different because the strength of the partial charges on these heteroatoms might be a little different. So, okay, that's one thing. But that would be like two sharp bands then, right? The other aspect is what we talked about. The distance can vary, and the angle of the OH bond relative to the heteroatom lone pair, and whether they're aligned in a perfect 180 degrees, in other words, a straight line, or whether they might be at different distances and angles relative to that OH vector, the vector of that bond. Okay? So that being the case, we have wide range of strengths of that bond, and so the resonance energy of that bond, right, these are like springs and they resonate at a particular frequency, are going to be different because that string strength is different. That is our evidence for hydrogen bonding, and also evidence for the variability of the strength of hydrogen bonds that we have. Now, other places where hydrogen bonds are important are in base pairing. So in DNA, our AT combination, right, is based on this alignment of these groups such that they give very good hydrogen bonds. Now notice the particular angles we have that are going on here. Okay, this is very interesting. You can see that these are going to be well aligned, right? The lone pair of electron on the nitrogen is directly over here, and it can be in a direct straight line across from this NH and its bond, right? Oxygen lone pairs in this oxygen, then with this NH. And then the same type of thing here, and now we have 3 hydrogen bonds, right? Beautifully spaced and set up for very good alignment. So not only are these multiple hydrogen bonds, right, and overall binding is a logarithmic function of the additive strength of each of these. So it's a more than just linear or more than just addition of these 3 bond strengths that leads to the overall bond strength. It's logarithmically related to it. Okay, so these are very, very good interactions, and they're also very specific because of this arrangement and this geometry, and hence why we have such good, efficient pairing of ATs and GCs, right? Alpha helices. Alpha helix is nothing more than a peptide backbone that is arranged in a helix, like a barber pole. Okay, an alpha helix is a type of helix that proteins can form that have a particular pitch to them, and they are a size of helix based on terms of its diameter as well as its rate of turn. Okay, so this is a well-defined structure within many proteins, if you remember from biochemistry. And amino acids are composed of, right, an amine group, a C alpha, which is the carbon that's between the nitrogen and the carbonyl, the carbonyl carbon, so C prime is the designation we have for that, C alpha, and then the side chain where we go C beta, delta gamma, and so on, depending on what the nature of that side chain group are, which is what we call R. And notice we're numbering these 1 to 9 because the amine terminus is actually at the top here, right? The first amino acid's down to here. This is a carbon, and it's kind of obscured to bond to its oxygen, right? The second amino acid is here, nitrogen, C alpha, C prime, and the side chain of the R2, and so on. And it goes around in a helical fashion down to 9. Now, where are hydrogen bonds? Our hydrogen bonds exist between, notice we have, let's do this one because it's a little easier to, what's the easiest one to see here? This is actually kind of interesting. So actually, even though this is behind, you can actually see the atoms the best. So in this R5 here, which is kind of on the back side of this helix. You can see it's nitrogen here. You can see the C alpha. You can see the C prime, and this oxygen here is its oxygen, right? So R5 is here. So the carbonyl oxygen lone pair are hydrogen bonded to the proton that's attached to this nitrogen of the amino acid R9. So it's 5 to 9. If we want to make a general term for this, we can say residue, and let's just call this the number I. Instead of saying 5, we're going to say this is I. And so R sub I is hydrogen bonded to amino acid, in this case R9. What would R9 be relative to 5? It's 4 larger, right? So if this is Ri, this is Ri plus 4. So what we are saying is we have a hydrogen bond between the I and I plus 4 amino acids. So when we talk about these types of hydrogen bonds and which groups they're bridging, that's often how we talk about them, an I to I plus 4 hydrogen bond. And that occurs between every single amino acid that is within this helix, except for the very first couple and the very last couple. Because as you'll see, each amino acid can be both an acceptor and a donor of a hydrogen bond, because each contains a nitrogen and a carbonyl group. Okay? So let's see, where's one that we have here that is involved in both? Well, our R5 again, right? Our R5, the nitrogen is involved in a hydrogen bond with what? This is the oxygen from R1. Again, I to I plus 4. Okay, so it's involved in one hydrogen bond on its nitrogen side, and on the carbonyl side, it's involved in another. Again, I to I plus 4, but now it's the carbonyl to the I plus 4 NH. And that takes place through the whole helix for as long as it proceeds. So if you're in the middle of the helix, right, you have 2 hydrogen bonds per amino acid. Now, if you're just in the first couple amino acids at the turn, right, the first couple, it's only the carbonyl groups that are involved in those hydrogen bonds, because these nitrogens, right, this presumably is not a helix up here. So therefore, they're not involved in those hydrogen bonds. So once we get to I plus 4, and then we get down to the last few amino acids. So again, as we end the alpha helix, the last few groups, the carbonyl groups, won't be involved in hydrogen bonds, right? Everything in the middle region will have both. So this is a major reason for the stability of this structure. And there's a lot of things about this structure that lead to its stability. We'll talk about it when we talk about amino acids and proteins. But this is one of the key features that we see. And alpha helices, when we look at total protein structure, are one of the substructures that we frequently see. One of the others, and one of the other most important, is the beta sheet. Beta sheets can be running in a parallel or anti-parallel in direction. And what we mean by that is that, for example, we see the nitrogen, C alpha carbon. So from N to C, we're running in this direction in the middle strand. In here, on this one, we notice that, oh, wait a minute, the nitrogen C alpha carbonyl is here, and it's running in the opposite direction. So when we look at these two strands, right, we can say they're anti-parallel, right? They're parallel to one another, but they're running in opposite directions. So we call it anti-parallel. So this type of a beta sheet with these molecules oriented like this, right, would be an anti-parallel beta sheet. We can have these parallel as well. We're just not really drawing that here. So it just looks a little bit different. Now, there's several interesting features about this. So now these are essentially extended. So if you notice, they're like long chains that are pulled out as long as they could be, kind of like if you're grabbing two ends of a string, right? And instead of it having all clumped up, right, it is stretched out. So we have this stretched out, and when we have it stretched out, notice we have this beautiful alignment and spacing for our hydrogen bonding that takes place. Kind of like you think about your DNA base pairing, right? It's kind of, you get a really good geometry for doing this. Now the other feature is, now that we have these hydrogen bonds stabilizing these two strings in this what would be a flat orientation, right? We put enough of these strings together, you can kind of see it's all in the plane of the screen. And what do we have? We have the side chains of every other amino acid pointing on one face. The amino acids in between those, and so again, every other amino acid in that sequence, are pacing in the opposite direction. So you can kind of say, if we number this, right, all the odd numbered amino acids have their side chains facing on one face, and all the even numbers have their side chain facing on the opposite face. This gives a sheet then, right, just like a sheet of paper, property that is dependent on the properties of these R groups. So one side of that sheet may have different properties than the other side of that sheet, which may be important for the function of the beta sheet itself, right? So you can imagine, let's just say we wanted one side to be polar and one side to be nonpolar. Well, we would have lipophilic side chains on one side, and we would have polar side chains on the other. And that would give it this character of a polar face and a nonpolar face on that sheet. So these are the types of things we see, again, in structural proteins. Okay, so that's enough for the hydrogen bond. Now we're talking about ion interactions, and ion interactions with quadrupoles, right? So we talked about ions interacting with dipoles, right? It wants to be nearest to the opposite charge within that dipole. Real simple, right? Same type of thing here. Now, for the most part, when we talk about quadrupoles, this is a depiction of a quadrupole, right? We have the electron density of that aromatic ring, right, the pi clouds, above and below the face of that ring. Around the periphery of that ring, if we have a concentration of minus charges here, where's the positive charges going to be? They're around the periphery of that ring in the plane of the ring. So we have a dipole, but it's kind of like two dipoles that are like back to back. So that's what these arrows are showing. We have our dipole oriented where our positive charges are here, and it goes out towards the direction where our negative charges are. So that's the direction of that part of the dipole. But then we also have negative charges on the opposite side. So yes, we still have the positive charges here, but it also then has a directional dipole in this direction. So we have this molecule that has multiple dipoles, kind of, or complex dipoles, if you wish, within the structure. So hence it gets the name quadrupole. So when we talk about aromatic rings and quadrupoles, this is what we're talking about. The other thing when we talk about a quadrupole, we're talking about this pi clouds. These pi clouds are negative. So sometimes these are called pi interactions. So notice these terms, right? Quadrupole and pi interactions are, you might see this term in one place or another in people using these. So you should be familiar with both of these terms. The cation now, a positive charge can interact with a negative charge, a partial negative charge, right? So various types of cations can basically be the ion that interact with a quadrupole. And where you will see that is they will sit above the ring where this minus electron cloud is. This is where they want to sit. Perfectly logical, right? They don't want to be where the positive charges are here on the side. They want to be where the negative charges are. And it could be above or below the ring, right? But it can only be one of them, right? Simply because this can only be in one place at a time, right? But it can be on either face of this ring. Okay, the experimental average is roughly 3 kilocalories per mole, which you'll see is a nice intermediate energy on that chart, right? And the types of things that we usually see are in a protein, arginine or lysine side chains. So this has a guanidine, which is always charged, a lysine, which is pretty much always charged, right? So these are cations, and they sit over the side chains of aromatic amino acids. So this is often seen in proteins. Now we can obviously have ions that are not, basically protonated bases, right, interacting with aromatics. That's a separate thing. But when we're talking about drugs and proteins, normally this is the type of interaction we're talking about, is with basically cations that are in the drug or in a protein, which would be on the side chains, as well as potentially the amine terminus, but there's usually more side chains, right? So in the case of lysine interacting with phenylalanine, tyrosine, or tryptophan, okay, so these are aromatic rings, so we're considering them all as, okay, just aromatic rings. So this, for this cation and these pies, right, what do we actually observe in crystal structures? So this is a picture of basically looking at 323 subunit proteins, right? So what are we looking at? We're looking at 323 different sites within proteins where cation-pi interactions take place. So the cation lys is shown, right, in these dots. Okay? The lysine and Phe interactions are blue circles. So if this is basically an aromatic ring of a phenylalanine, if instead of a phenylalanine we have this extra OH on it, so it's a tyrosine, those are the red dots. Okay, so you can notice that they're both fairly similar, but some of the red dots are maybe over a little more closer to where the oxygen is in the tyrosine, right? Because the electron density of the pi orbital, and then of course you have lone pairs of electrons on this OH, right, kind of skew it over in this direction. So you can see that where the lysine residues want to be in tyrosine and where they want to be in phenylalanine are largely overlapped above and below the ring. And on top of that, right, they're a certain distance away. Why are they a distance away? Because, right, our material here and our material here has certain van der Waals radii, right? So they can't be overlapping. They have to be at a particular bonding distance. So you can see they're accumulated at a certain distance range. And if they're farther away from this, are they even interacting, right? Because as we get farther away, the interactions get weaker and weaker, right? So they're going to tend to accumulate near this van der Waals distance range. Notice the spacing here is the same as the spacing here. So you have that, and of course where the electron density is going to be the greatest, so hence skewing a little bit of the red dots here towards where the OH is. The OH doesn't exist in the phenylalanine, so the blue dots naturally are going to be just over these white rings. Okay, which is the phenylalanine ring. Now, this is just looking from a different projection, and so this is for the lysine tryptophan interactions. Tryptophan is a heterocycle, right? So we have a 5-membered ring with a nitrogen, and that lone pair of electrons is part of the aromatic system. So this is not basic. And it leads then to these 10 electrons in this ring, right, making this aromatic. So actually the pi cloud is over this whole ring. Notice that our lysine cations are over this, but they're actually more centered to being over the 6-membered portion of the ring rather than the 5. So why would this be? Well, this has to do with the electron density around the ring for one, but it also has to do with something that you actually cannot see. And what we're not seeing here is the rest of the protein that this tryptophan is part of, right? And because this is basically a composite of many, many different tryptophans from these 323, right, single units. So what is attached here is going to be different in each one of those tryptophans that is being compiled here. But basically there is steric bulk over here. In other words, these lysine residues might not be able to sterically be over here even if they electronically wanted to be. They can't because of steric hindrance. Okay? So you have two aspects going on here with regard to where the lysines can be. It has to be accessible three-dimensionally, and it also then is over the place where the electron density is the highest. So this has those things shown here. Notice also here the attachment point, right, for this phenylalanine ring is going to be over here. So there's protein over here, right? So these charges also cannot be over here and, stray ones distributed in this direction, because very simply they sterically cannot occupy that space because there's other parts of the protein here. So again, that's another reason why you see these tending more to the left side here than directly centered over the top of it. Now, this is just some individual pictures of a cation-pi interaction. This one's actually kind of interesting because it's complex. So this is a review article here on these types of interactions. And it's showing a lysine side chain. So this is just the amine portion of a lysine side chain. And where it basically resides in this protein glycoamylase crystal structure relative to aromatic side chains at position 50, 52, 116, and 120. So these are the aromatic rings, right? This is a tryptophan, this is a tyrosine, this is another tyrosine, and this is another tryptophan. It is basically interacting in a cation-pi interaction with each of these 4 aromatics. So cation-pi, 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 right? The cation is a cation, and its attractive forces are in all directions three-dimensionally around it, like wherever it's not attached to something, which is like the rest of the side chain and the peptide that the lysine's attached to, right? But it's way out on the end of a chain, so it's very accessible. And it's interacting with the flat faces of the aromatic rings. Okay, very simple. So this is actually showing 4 different interactions. That being the case, look at the interaction energy that they're basically calculating for this, 22 kilocalories per mole. Why is it? Well, it's 4 interactions, right? So they basically add up to a stronger interaction energy, as you do with any other type of molecular interaction, is we add these binding energies together. Now, how they affect affinity, right, an equilibrium constant, is a logarithmic relationship. But in terms of binding energy, it's just completely additive. So we add the energy of this, we add the energy of this to this, and the energy of this, and that's how we get to 22. Another place that these can exist, and that actually may be part of what we see here, because we don't know the structure that these tyrosines and tryptophanes are in. They could be in helices, and this lysine, I don't know for a fact because I don't see a number for it, could be adjacent in a helix to one of these. I don't know. But what we can see is something like we have a cationic side chain, so an arginine or a lys, that exists, again, 4 amino acids away. Actually, it could be 3 or 4. I plus 3 interactions are also fairly close. So remember, what we're saying is, in terms of the numbering, this is an interaction here with residue 79. And we have 80, 81, 82, and 83 is this tyrosine. So this is an I to I plus 4 interaction of the side chains. And the reason why we see this I to I plus 4 is because in the helix, so this is showing the backbone of a helix just depicted as a ribbon, the side chains come off of that alpha helix in basically all directions, right? Depending on where that amino acid is on the ribbon, right? Some will be poking, if it's here in the ribbon, it's looking at you. If it's here in the ribbon, that side chain will be pointing away. If it's here in the ribbon, it would be pointing upwards, right? So there's side chains all around this central core, this amide core that's helical. And they come off where in such a way that every fourth residue, these side chains are on the same face of the alpha helix. Now they're spaced in such a way that these side chains, which have some flexibility, can potentially interact with one another. And so if we have the cation here on the arginine side chain, which is a guanido group, so a guanidinium, when it's protonated, can interact with the flat face and the pi cloud of this tyrosine residue, giving us a cation pi interaction. You don't have to memorize these numbers for these examples, right? This is just basically showing you examples of how this is real, what the values are that we actually do observe, and you can see they're variable. We see different numbers, which is why ranges were given on that first summary chart of the different types of molecular interactions. Again, what is the variability due to? It's due to the orientation and the distance of these. The orientation is going to affect the distance, so notice our guanidine, which is a planar molecule, is kind of parallel to the aromatic ring. In other words, the two flat faces of these are interacting. Why? Because kind of like if these were two hands, right? If one was edge on, it couldn't get as close as if you have the two faces of your palm facing one another, and they can then get really close to one another. So that's what we have. Now, this is a material, okay, the drug Aricept, binding to acetylcholinesterase. Okay, so this is an inhibitor of an enzyme. The enzyme active site here consists of this tryptophan residue, this tryptophan residue here at position 84, and this phenylalanine at 330. There's water molecules involved in the bound drug interaction, right? If the drug's not here, right, water occupies the site, and then this has to displace that water to bind to the enzyme. Where we see cation pi interactions, these are ion quadrupole. Where's our ion? Our ion's here, and it's interacting with the pi cloud of this phenylalanine 330. This is an ion quadrupole. Or by pi-pi stacking. So we have quadrupole interaction. The two flat faces of these now are not going to interact very well. And we're going to talk about quadrupole interactions. Flat faces do not interact well. So this is not drawn super accurately because this kind of looks like they're flat face to flat face. If you think about it, you would end up with a minus charge sitting over a minus charge. Not good. What we have is you have a minus charge in the flat face here, and it's going to interact with some aspect of the edge of this other aromatic ring, right? And there's a couple of ways you can do that. So we're going to show quadrupole interactions and the way they can interact, but just be aware that it's not going to be perfectly face-to-face. It'll be either be offset or perpendicular to one another, right? So those are what we would call the quadrupole or pi-pi interactions, and such as we also have here. And this is basically showing a dipole. So in this case, in OH, we have a partial positive charge on the hydrogen interacting with the pi cloud negative charge, partial negative charge, right? So this is not a hydrogen bond. Don't want to confuse it with that. I know we're showing these hatches. In this case, the hatches here do not designate hydrogen bonds. They are designating just interactions. The hydrogen bond that we have is actually between this water molecule that is hydrogen bonded to this hydrogen molecule of this water. So we have two waters here. And this oxygen is hydrogen bonded to the hydrogen of this iminium that is in here. Now, we're also, just to be complete here, since this is an ion, this ion will also potentially interact with water as a dipole. That's not what's being shown here. Notice it's the negative part here of this interacting specifically as a hydrogen bond. But the negative portion, right, of the water, the partial negative charge on this oxygen, is going to have a certain attraction to just the ion aspect of this. So that's one thing when we talk about molecular interactions. Sometimes we can have multiple things going on, and we say, well, what is the interaction that is taking place here, right? The way we usually describe it is we describe it in terms of what is the strongest of those multiple interactions that it is involved in. Is the ion dipole stronger than the hydrogen bond, or the hydrogen bond stronger than the ion dipole interaction, right? So these are the types of things that become very difficult to say at some point. So again, we have a relatively simple subject, but reality is often much more complex than the way we have to try to simplify things to describe them. Okay, so cation pi is also ion quadrupole, pi-pi, quadrupole, and our OH pi interaction is a dipole quadrupole. Now, as we said, we don't want our partially minus portion of our pi cloud interacting with another pi cloud directly, right? That's going to lead to repulsion. So, aromatic systems like this can be either oriented edge to face, which we actually do observe. So the edge is this region where we have the slight positive charge, right? So that's what's going to be on the edge. And that can then sit over the face where the pi site negative charge is. So you can imagine we have a partial positive and a partial negative charge interacting. Cool. What do we have here? In face-to-face, they're not sitting directly over each other. What they are is they're offset. If we offset the aromatic rings, now what we have is the center of the minus charge region, right, is basically in closest approach to the positively charged region of the other aromatic molecule, right, the edge here. So again, the edge here is interacting with the face of this, and the edge here is interacting with the face of this. So they're being complementary to each other in both directions, right? This is only contributing one interaction, right? It's the positive to negative. And this is the positive to negative and the positive to negative. So this is giving two interactions. Now you can argue about, well, what's the relative strength of this versus the relative strength of these, right? There is some back and forth with regard to that. So these both do occur. They're both attractive forces. This is repulsive, so therefore it doesn't happen. And so when we talk about these things that look like face-to-face interaction, we talk about, right, intercalation. When we talk about DNA and drugs which interact with DNA, they have to interact like this, right? So it looks like, oh yeah, they're parallel or face-to-face, but they have to take into account these charge differences, and that's more optimal. Okay. Dispersion interactions. So Fritz London, it's not named for the city, it's named for this physicist, basically described how we can have an induced dipole. So what you have are temporary dipoles that exist within any molecule or atom. And let's just say that's what we have here in the structure on the right that is moving back and forth, okay? So at any moment in time, an electron is going to tend to be concentrated on one side of the molecule versus the other, just randomly. Now these things obviously move around very quickly. So on average, they're kind of like over it, and we define that as that's what the van der Waals radius and the cloud is, right? The electron cloud. But at any point in time, at any instant, right, it has to exist somewhere. So if that's somewhere, at a point in time when it comes close to another neutral molecule, right, so this electron can be all over the place, what's going to happen is the electron in this one, as it gets close, is going to tend to push the electrons in this second one away from it. And what that's going to do, it's going to take a non-ionized material, right, a non-dipolar molecule, and induce a dipole in it. So the way it can be described is these fluctuations create a temporary dipole, and that temporary dipole in the presence of other molecules creates an induced dipole. That allows for an interaction between them, because what we have now are these two molecules with these partial charges, and they can align opposite to one another, and now we have a potential attractive force between two molecules that were otherwise neutral, and essentially uncharged materials do not attract one another. So it is only these induced partial charges that give us our attractive force in things like alkanes. So Fritz London described this, and hence this interaction gets his name. But the general non-named version for this is induced dipole, induced dipole. It's very weak, but since we have so many uncharged residues that interact, right, with other uncharged residues between the protein and the drug, these very small interactions cumulatively add up. So we might have 20 carbons interacting, right, with a receptor. We would have 20 of these interactions, whereas opposed to an ion, we might only have one ion in the entire molecule. So while the ion interaction is strong by itself and contributes a good amount, the amount that we get from these induced dipole interactions can actually be quite large, and actually larger than the ionic interaction if there's enough of these to add up to an amount that's greater than the ion interaction. Okay? So it's not just the strength, but it's also the quantity, because we have this feature of the additivity of the partial attractives, the partial binding energies that lead to the total binding energy. Okay. Now, one consequence we have of this interaction only takes place when the two molecules are in direct contact with one another. The second we separate these at all in the slightest way, we lose these interactions, right? So if we are matching, say, a alkyl group within a lipophilic pocket of a protein, the best interaction we get by doing that is to completely fill that pocket with, say, an alkyl side chain of the right shape that fills it completely and doesn't leave gaps and doesn't leave holes. And that will give us the strongest interaction. So that's kind of what's shown here. We kind of have a pocket here, right? And we have basically groups that protrude out and match that shape. So this matched shape is very important in many type of drug interactions in terms of getting a good fit, and that leading then to a very good binding energy. Now, there's upsides and downsides to this. The upside is, one, look at all of the different interactions we get from this, because it is making contact with so many things. In fact, one atom could be making contact with multiple atoms, right, of the receptor. And so we can get very strong interactions from this. If we have any imperfection of this, now imperfections, let's just say this atom was missing, would just lead to a reduction in the overall binding energy, because there would be fewer of these interactions, right? These interactions are shown by these lines. So we would still have this line, this line, this line, this line, and so on. We'd have all of these, but we would be missing these three lines. So the overall binding energy, right, is the sum of all of those little lines. So it would just be a smaller sum because it would have fewer of these energies being added in. If we modify that now and put this group back in here, we can see, boom, we now pick up these, and now we've increased the binding energy by the magnitude of these three bonds relative to all of these other sum, right? The total increases fractionally above what it was before. Now, here we get to the point where, what's the downside of this? The downside of this is that this is extremely specific. If we now take this and, say we're operating kind of blindly, which we often do when we're trying to do drug design, and say, okay, we added this group in here, let's make it even a little bigger, because we don't know if the pocket's any bigger or not, right? If we added another atom on here, it would be like over here. Well, now what is that going to do? Well, it can't occupy the same space as where the receptor is occupying. So it's going to push this entire molecule away. In other words, this molecule cannot match these surfaces as well because it has this huge bump sticking out of it, right? It would be kind of like if you have two panes of glass. If you've ever taken two panes of glass, particularly if you put a drop of water on it or something, and put them together, they will adhere to each other. Even without the water, they will adhere to each other. And sometimes if you try to separate those two panes of glasses, it can actually be quite difficult. Now, if you take those two pieces of glass, and before you put them together, you put a marble in between, or it doesn't have to be anything as big as a marble. You could put, like a small pebble, right? Just anything small, grain of sand for that matter, right? It will prevent those surfaces from perfectly matching. And now you can very easily lift that second pane of glass out of the other because it doesn't have that many points of contact, so the adhesion between those two surfaces is small. Why do we have adhesion between two perfect panes of glass against one another? Because they're actually made of silicon dioxide, right? And so they're essentially polar materials, and we're putting one polar surface against another, and they can all then have these very strong molecular interactions, even though they're not in solution, they're solids, right? They can still have that interaction. It's called adhesion. Once we put anything that prevents that perfect shape match between the two, like the grain of sand on the pane of glass or a little pebble, right? It prevents all of those surfaces from perfectly aligning, right? It provides a gap in between, and therefore we don't get that binding, right? We can lift that second pane of glass off of it very easily. So that's the type of situation that we're talking about. Steric match becomes absolutely critical. So remember, this interaction, and this is an important thing to remember, requires intimate contact, complementary shape matching, and because the distance dependence of the strength of the interaction drops off dramatically, 1 over r to the 6th, with distance, as soon as we get any separation between these two molecules, we no longer have an interaction between them. Okay, so this is in complete contrast to our ion-ion interactions, which can interact over the greatest distance, right? And they're completely dependent on the two charges being able to see one another. As the distance changes, it drops off by a factor of 1 over 2, r to the 2. And we can have basically shielding interactions from solvents. Here, the interaction energy drops off quickly even before we get to the point of worrying about shielding interactions from solvents, right? Solvents can do that as well because solvents will interact with these surfaces. But in these cases, we don't even get any interaction if they're separated in any way, shape, or form. So the nature of the solvent, in other words, that dipole, remember we talked about that index that we had, which was greater for water than it was for hexane. It wouldn't matter what the solvent was in between here. Any solvent that is in between these two molecules means there will be no interaction between the two. Okay, so that's the difference. Induced dipole interactions are the most distance sensitive, and they require intimate contact. Ion-ion interactions can interact over the greatest distance. Everything else that has a partial charge in between in our list of molecular interactions, right, is going to fall somewhere in between those two. Now, the hydrophobic effect. You'll see people talking about hydrophobic force and things like this. There is no such thing as a force going on here. This is literally an effect. And it's an effect of certain types of materials that are interacting with one another, particularly in aqueous systems. So we will talk about hydrophobic effect as being important for things like protein folding, basically, the idea of if we have oil and water and we mix them, right, you get a bunch of little beads of oil in the water and then eventually they coalesce and separate. That is due to the hydrophobic effect. Now, what does it come from? So these are oils, right? These dots, these are hydrophobic groups. And if we shake up our oil in the water, right, it is in water. These little wedged things are waters, okay? Oxygen, hydrogen, hydrogen. And they are separated from each other. So this hydrophobic group is not interacting with this hydrophobic group. Each is interacting separately with only water. And water can interact with itself quite well because it's a dipole, right? And we can get dipole-dipole interactions with itself. It can hydrogen bond to itself. And it interacts less well with hydrocarbons than it interacts with itself. But it can interact with hydrocarbons. And what it tends to do is when it hits a surface like this, just like it happens on the surface of water, right? And what's above water? Air, right? Air is essentially hydrophobic. And so what it does is water organizes itself on the surface of water, which gives us surface tension. Here we have a hydrophobic group within the water solution. And so the water tends to form a cage, right, and organize itself around that hydrophobic group. Okay, this can also be the case of where we have a hydrophobic group, say, of a protein sticking out into water, right? The water will organize itself around that group in such a way. So we have this organized water versus relatively disorganized water. Okay, so what do we have that happens then over time? Well, obviously these things diffuse through solution in their little cages, right? And we can imagine, a path of, this thing wandering around here and finding this other one and bumping into it. What then happens, right? Well, these cages are not, these are, hydrogen bonded, associated water molecules to another. So they're not covalent bonds. And they interchange all the time with the other hydrogen bonds that exist with the other parts of the water solution, right? So these are constantly interchanging. They're kind of like cages, but they're not cages from the standpoint of these things are linked like a chain link. They're kind of like the type of thing if you have a magnet and you had iron filings on the top of it, right? They cover the magnet, but you can push aside those iron filings, right? And get to the surface of the magnet, right? It's kind of like that. They are organized around it, but they're not like a permanent wire cage around it. So when these things come together, physically just through diffusion, these things are always bouncing around in solution, right? They would bounce around, and with a certain amount of energy would hit each other, and the cage that on the two facing sides of each other can basically be pushed aside, just kind of like what we were talking about on the magnet, where we can push aside those iron filings. And now these two hydrophobic surfaces can interact with one another. Now, the affinity we have for a hydrophobic group and a hydrophobic group is going to be based on an induced dipole interaction, depending on the nature of it, right? Say if you could say, oh well, something like benzene is hydrophobic, and so these could be benzene rings. Okay, so now these could be involved, say, in a pi-pi interaction or something like that, right? So okay, you can have various types of ways that hydrophobic groups can interact with each other, but it's not the same as the way it's interacting with water. So anyways, that would have a particular strength, just like the interaction of the water with the hydrophobic group has a particular strength. Now, what we've done is we've moved this cage around. And if you remember the principle that's used in packaging, what is the most efficient way to contain an object, right? The most efficient way that has the least surface area with it for a particular volume of an object is a sphere. So basically, if we're containing multiple hydrophobic molecules within water, this cage will become sphere-like, right? So here we have a sphere with a certain surface area. Here we have a sphere with a certain surface area. If we combine the hydrophobic groups together, right, we now create a different surface area of a, quote, sphere around it, right? This is not a perfect sphere, but as it gets bigger and bigger, it approximates it better, right? Then what we have, right, is more efficient packing in this one sphere versus these two separate ones. There are less waters associated around this hydrophobic material than when they are separately packaged. And then this package, right, could meet either another one of these single ones, or it could meet another one of these double packages in the solution, and they become bigger and bigger and bigger and bigger until ultimately we get a complete separation of the two layers. Okay? Or we have as much of this hydrophobic material associated with itself and separated from the water, right? This is the type of thing where we get the small tiny beads of oil in water, right? When we shake it up, we've added energy to it. And then over time, as we let it sit, we see the beads getting bigger and bigger of the oil, right? And then eventually those beads separate out into a whole complete separate layer, right? These things then will float to the top and become a layer. So this is your salad dressing type of thing, right? And so what is happening here is we're essentially more efficiently creating a separation between the amount of water that needs to be organized around the hydrophobic material versus what was needed in this other situation. Okay, so what is going on? We have several things. We have the interaction between the hydrophobic material and the water. That has a particular strength. We have the interaction energy between water and water. We have the interaction energy between the hydrophobic material and the other hydrophobic material, right? And what we're saying is we don't have hydrophobic here, okay? And we do here. So the energy that's added here is like a plus, right? We have more of that type of energy added here. But as we go from here to here, we have more of the water hydrophobic interaction taking place than we have here because we have fewer of the waters associated around the surface of this, right? And eventually in the middle of this, as this gets bigger, we're going to have a lot of hydrophobic material that isn't even touching the cage, right? It's just within a glob of other hydrophobic material. So we are decreasing the number of interactions that we have between the water and the hydrocarbon. Okay, so that would be a minus. So one interaction type is a plus, one interaction is a minus. What else is going on? Well, when we are no longer needing water molecules around this, right, we are freeing them up into solution and they become more random. Right? There's some organization that takes place out here, but it's nowhere near the amount of organization in this shell around the hydrophobic. Now that it's more random, that gives us a property called entropy, and entropy increases. When we want to consider out the overall energy of the systems, right, we have to take into account the binding energies, which we call enthalpy, and that's, you know, binding energy between the two hydrophobics versus the hydrophobic in the water. We have those enthalpies that we have to take, and we have to take into account entropy. Now, when we do this process, the entropy of the solvent that is gained by going to system B is greater, okay, than we have in this system, and it also basically is sufficiently large that it counteracts the enthalpy changes that we get between these two types of interactions, such that overall the energy of this system is more favorable than the energy of this system. So, if we want to quantify this, our enthalpy for the hydrocarbons are attracted to one another, and that's of a certain value. Okay? The strength of a water-water interaction is greater, right? It likes itself more than water hydrocarbon, right? So dipole-dipole is greater than dipole-induced dipole, right? This is induced dipole, or as we said, maybe it's a weaker dipole, right? If it's an aromatic or something like that. We're talking about hydrocarbons here, so for the most part, we're talking about, alkane type of things. So we get that. So that's an enthalpy and that's an enthalpy. And we get this entropic effect. Since there are fewer waters organized around the hydrocarbons in this situation, we get an increase in entropy going from here to here. And as we know, nature likes increasing entropy. It is a force, and is a quantifiable force when we talk about energy, right? It's T delta S. So we have our delta G equals, right, our enthalpies, our delta H's, minus the temperature in degrees Kelvin, right, and the change in entropy. So they work in opposite directions, right? Increasing enthalpy is good, increasing entropy is good, but in terms of how they affect the binding energy, they are different, right? So increasing entropy and increasing enthalpy are both things which will then affect our binding energy. Okay, so this is the definition of a hydrophobic effect. And if we want to say it without talking about all of the thermodynamics, the quickest way it can be described is the driving force for the hydrophobic effect is the increase in entropy that we get, okay, when our hydrophobic portions of a molecule are separated from the water as much as possible. That is probably the simplest way to talk about the hydrophobic effect. It's entropy driven. It is not driven by the binding strength. Okay? The ability of water to interact with the hydrocarbon is greater than the enthalpy of the hydrocarbon interacting with the hydrocarbon. So we're losing the enthalpy of the water versus hydrocarbon because we have fewer of them here. So you would think that would be unfavorable if you did it only based on enthalpy considerations, right? So clearly what's happening, this is not an enthalpy molecular interaction energy effect. This is an entropy effect. And that's why we're saying it's not a force. Okay, this is just another excerpt from a book. Okay, and what it amounts to is just another description. As a result of the acquisition of structure, which means the aggregation of hydrophobic materials together and away from water, where there is the minimum amount of water, right, that is including this in a cage. As a result of the acquisition of that structure, the entropy of water decreases, okay? And the dispersion of the hydrophobic molecule into water is entropy opposed, okay? So what does this say? Dispersal of the hydrophobic molecule. In other words, spreading these out into water, and which creates more cages. The last part of this is the important part. It's coalescence. So in other words, the coming together of hydrophobic molecules to the exclusion of water. The coalescence is entropy favored. And this is the driving force. So I think the previous slide's a little clearer. This is from a textbook though, and this is how they're trying to present this information to explain it. So as you can see, it's a concept that's a little counterintuitive, but if we just understand the entropy aspect, that's where we're going. Okay, and what does that mean? Well, it is something that is actually important for how proteins get their shape, because proteins have side chains. They have side chains that can be ionized, they can be polar, they can be aromatic, they can be involved in ion-ion interactions, ion-dipole interactions. We can have covalent bonds between side chains if we oxidize this to form a disulfide. We can have alkanes and other aromatic hydrocarbons come together. We can have alkanes and other alkanes side chains come together. And each of these is a different type of interaction that can lead to the stability and formation of the shape of a protein. And so this is how we get our alpha helices, beta sheets, and then and various types of turns, which have to exist in order to make a shaped molecule or protein, or in some cases enzymes or receptors. And so there's many types of interactions that we can have. We can see just some of these. So this is a covalent bond, a disulfide, which gives a lot of stability to the material. This is an ion dipole. So we have an ion, a minus charge, and the dipole, is with the OH, because that is a dipole. And it's also combined with a hydrogen bond. So we saw that before with that aminium, and the water molecule. This is a carboxylate anion and an OH of a tyrosine. This is an ion-ion bond. Again, the ion bonds are much stronger than hydrogen bonds, but you can also see how we can have oxygens, lone pairs, interacting with the hydrogens on that nitrogen. So they can be involved in hydrogen bonds as well. We can have induced dipole, which are van der Waals interactions, and quadrupole induced dipoles, which, since there's no ion in the word, remember these are also considered van der Waals interactions.